Hello and welcome to part 9 of Dev Maths and Stats course lecture 2, in which we take a quick look at implicit differentiation before moving on to some applications of this lecture's methods. So, now this is a kind of trick which is based on the chain rule. So when we're differentiating, normally we're trying to find dy by dx. But it's not always necessary to have an explicit function to start with where y is equal to something. So you don't always have to start with y equals something, something, something to get to the derivative. For example, something like this. If you start with an equation like this and you want to find dy by dx, it would be quite hard to rearrange this and make y the subject. You could do it, but it would be very messy, and then you would have to differentiate something very difficult. But you can still find an expression for dy by dx without having to do it. So what you do is you use all the rules that we've had already, plus whenever you meet a term in y, when you differentiate something in y, you use the chain rule. So to start with this one, we just go through and differentiate each term. So you might have to check back over some of the previous rules, but in this example, this first one here is going to be the product rule. So we're going to do this and this. So 5x squared gives you 10x, and this you leave alone. And then you leave this part alone, 5x squared, differentiates y. Now, differentiating y with respect to x, well, you can't do that, but you can differentiate y with respect to y, it just becomes 1. And then the chain rule says that to convert from d by dy to d by dx, you multiply by this. So you multiply by dy by dx, which converts it from derivative with respect to y into derivative with respect to x. And then come to this part here, so minus, that's a minus sign there. Differentiate this, so it's 8y, but that's differentiating with respect to y. So to convert it into with respect to x, you multiply by dy by dx. And then this e to the x just differentiates to this. So you use exactly the same rules as before, but every time the variable is y, you then multiply by dy by dx. Okay, so once you got to this stage, the thing you are trying to find out is this, dy by dx. So you imagine that's an unknown, and you rearrange it, and you solve the equation for this to find dy by dx is equal to this. So what's happening here is I've taken this to this side of the equation, so you have this bit here. Then I've factorised, so taking this out as a common factor, I'm left with this minus this, and divide by that. I'll give you more detail when I go through examples in a minute. What you usually find is that when you get dy by dx, that on this side there's both x and y, rather than only x. So that's why it's called implicit differentiation, because it's not, you don't get an explicit outcome in terms of the derivative, in terms of x. So here, if we knew the values of x and y, that would let us work out the derivative. Okay, you'll see some examples of this in the applications, so feel free to move on to those. If you think you need some practice, then try these, and I'll now go through these in the usual way by hand. So you can either follow these or you can skip through, up to you. So here's the first one. So 2y to the power 3, 2y cubed, e to the x equals 4 that looks wrong. Yes, I think we've... Oops. This should be to the power 7, otherwise it doesn't make any sense. Well, it does, but it's... So as I originally wrote this, it would be just 4 times 7 would be 28, which wouldn't be a very interesting problem. So 4x to the power 7. So here we're going to find an implicit expression for dy by dx. So we just differentiate both sides with respect to x. So taking this one, we go through term by term. So first we're going to use the product rule with this and this. So differentiate this and leave this alone. So that's 6y squared. 6y squared times e to the x. But we are differentiating with respect to x, so this variable is y, so we have to multiply by dy by dx. Because the thinking is, if you have something and you want to differentiate that with respect to y, then what you have to do is differentiate with respect to, we want to differentiate with respect to x. But if this has got only y's in there, then we can differentiate with respect to y. So that's what I did here. 2y cubed gives me 6y squared. But then you must multiply by dy by dx. So every time I see some y's, I need to differentiate. I can't differentiate directly with respect to x. I differentiate with respect to y and then multiply by this. So that's what I've done here. So far over here, I have differentiated this part and left this unchanged. Now the second part of the product rule is that I have to add. This now stays the same. And I differentiate this one. So the differential of this is just unchanged. And now I don't have to multiply by anything because this is already in x. And over this side again it's in x, so you can just do 28 x to the power 6, and there's no need to multiply by anything because it's already x. So now we've done the differentiation, but what we're interested in is this here. So we need to find this on its own. So what we do is we'd 28x to the power 6, subtract this from both sides, so this disappears and it comes to here. So I've moved this there. Now I'm left with this. So I could divide by that. So dy by dx is going to be all of this divided by 6y squared e to the power x. And then you can simplify just a little bit and let's save space just by doing it like this. This can be 14. This can disappear, and this can be 3, just by cancelling. Okay, so that gives you an expression of dy by dx. It's implicit because on this side we have y's and x's. Okay, so the command for this in Maple is that. So hopefully that's more or less the same thing. It's not very, it doesn't cancel out very much. 114. Yes, it has. It's just written the other way around. Okay, so it seems to agree. Oops. Huh. Interesting, it's written it differently. Okay, please ask if you have any questions about that one. I'll go on to the next question. Next example. So we have 6y log x equals x to the power 7 over y. 6y log x equals x to the power 7 over y. Okay. Just try and make it a bit tidier. 6y. So we go through step by step. So here again, product rule. So we have to differentiate each one in turn. So 6y differentiated just gives 6 log x. That's with respect to y, so I have to multiply by dy by dx. plus, then 6y is left alone. Differentiate log x, I get 1 over x. This is already a term in x, so we don't bring in this. Then the right hand side, here we can practice the quotient rule. So we differentiate the top, so 7x to the power 6 times the bottom, y, minus, because it's quotient rule, this stays the same, x to the power 7. Differentiate y, you just get 1. It's 1. But then you have to multiply by dy by dx. That's the top part. And then it's quotient rule, so we also have to divide by the bottom squared, which is y squared. So this looks a bit unfriendly. So the first thing would be to multiply both sides by y squared. Oops. Let's multiply by y squared, multiply by y squared equals 7x power 6 y minus 7. Oops. And so that's removed this fraction. Now it's getting closer to the initial example in this section. Now I want to move everything with dy to this side. So on this side I'm going to have, I don't want to try and fit it on the screen, so we'll have dy by dx times 6y squared log x. That's this part. And also dy by dx, when we add this on here, as this comes to this side, it'll be positive. So plus x to the power 7. So this gives you that expression. This times this gives you this expression on the left hand side. Oops. Then this, I'll take to this side by subtracting it. So this is 7x to the power 6 y minus 6y cubed over x. Yeah, I think then at this stage, maybe to make it more tidy, so I can fit it in, I would also multiply by x. So if I multiply by x here, multiply by x here, so it becomes x to the power 7, then that clears that. So 7x to the power 7 minus 6y cubed. This is all multiplied by x now. And then finally you just divide, so dy by dx is equal to 7x to the power 7y minus 6y cubed. That's this part, divided by, let's write this more neatly with x on the right hand side, 6y squared log x plus x power 7. And there you have it. So a very, very messy looking expression. But you have at least got the expression for dy by dx. So this is useful in things like computational methods when you have a computer which is doing these sums. So it doesn't matter if it's complicated. You have the values of x and y. You just want to know what this derivative is. How is y changing when x changes? Plug the numbers into this using a computer or a spreadsheet and you'll get an answer. But for algebraically, it's horrible. Let's just see if there's anything like, which it gets harder and harder to compare answers here. But I think you can see that's clearly exactly the same thing. Okay. And then finally onto the last example in this section, which is this one. visible. So it's got exponentials and logs. So 5 e to the y log y equals x. It's a strange looking one, but we can use the same rules, go through term by term. This time this and this are both y's, expressions in y, so when you differentiate each of these we have to multiply by dy by dx. So doing this one first, we have 5 e to the y stays the same, log y dy by dx, plus, and then 5 e to the y, that stays the same here. This becomes 1 over y, that's for the log, that's 1 over y, times dy by dx. And this just becomes 1. And that's fairly easy to rearrange this, because dy by dx is equal to 1. We just factorise all these things out, so we put brackets here, this and this is inside the bracket, so there's also a 5 actually, isn't there? Should bring the 5 out, so 5 e to the y log y plus 1 over y. That's these two terms here. And you can then multiply by y to simplify it a bit better, also to make it look nicer. So, are we anywhere near? There's a y on top here because the final step might be multiplied by y, as I said, so you have a y here, you have a y there, this would go, and you have a y here. If you multiply by y, multiply by y, yeah, so that gives you the same form. Excellent. Okay, so as always, questions very welcome. And in the next video we'll move on to this last section here, looking at some applications of the methods from today's lecture. Thanks for watching.